Imagine trying to clone a living, breathing human being, but instead of getting a blank slate infant, you get a full-grown adult.
Right, an adult who totally insists they are the actual original person.
Exactly. They have the exact same memories, the same social security number, and like within 5 minutes of existing, they're trying to log into your bank account and text your mother.
Just absolute chaos.
Yeah, chaos. But today, we're looking at why computer programming faces this exact same identity crisis when it tries to duplicate data, and more importantly, how you can seize control of the machinery to fix it.
It really is a massive issue in software.
It is. So welcome to today's deep dive into Aaron Rose's article, The Secret Life of Python Deep Copy. Our mission today is to basically unlock the hidden mechanics of Python's cloning process. We want to take you from being just a passive user of the code to an active partner who dictates exactly how digital objects are born.
And it's such a brilliant deep dive into software architecture, largely because of how the author frames it. I mean, we aren't just reading a dry technical manual here.
No, definitely not.
We are dropped straight into this really vivid narrative setting. It's this grand Victorian library in London. Imagine dark mahogany desks, towering shelves full of books, the quiet ticking of a grandfather clock in the background.
Oh, I love that vibe. It's so atmospheric.
Right. And we follow a senior software engineer named Margaret and her junior colleague, Timothy.
That setting creates such a specific mood for the whole piece.
Yeah.
Like they aren't in some chaotic, neon-lit startup rushing to push broken code to production.
No, they are in an environment where craftsmanship is just the unspoken law. Code quality is all that matters.
Exactly. You don't just write code that miraculously compiles and call it a day. You write code where you understand every single gear turning beneath the surface.
Which is so rare these days.
It really is. And for you listening, whether you are managing a massive, messy code base where bugs keep mysteriously appearing, or you're just insanely curious about how digital replication actually works under the hood, understanding this concept transforms how you think about software.
It fundamentally shifts how you interact with the software you build. You stop being a passive user and become an active architect.
So true. To understand that shift, though, we have to look at the roadblock Timothy hits in the story.
Right, his current project. He's building a system for a local chess club. Specifically, he's working on a tournament session class.
And this isn't just a simple string of text, right?
Oh no, not at all. A chess tournament session is a really heavy, complex data structure. It holds player profiles, historical move logs, the current board state.
A lot of data to juggle.
It is. And crucially, it tracks the exact start time of the match and a completely unique session ID.
Okay, let's unpack this. Because normally a deep copy is exactly what we want, right? Like if I'm copying a file, I want the exact file.
You want an identical twin.
Yeah. If I'm duplicating a nested JSON payload or copying a complex configuration file, I want a perfect isolated replica. I want identical data. So why is Timothy suddenly treating an identical twin as a bug rather than a feature?
What's fascinating here is how Margaret frames his confusion. She tells him he has stumbled into the perfect clone problem.
The perfect clone problem, I like that.
Yeah, you are spot on that an identical twin is usually the goal of a backup. But context dictates everything. Timothy isn't just archiving a finished game to a database.
Right, he's trying to copy a match that's still happening.
Exactly. He is trying to take an ongoing match and branch it off.
Oh, like a what-if scenario.
Yeah.
So player A is about to make a risky move, and they want to branch the board state to see how it plays out without ruining the main game.
That's the exact use case. But if he uses Python's default cloning tool to create that new branch, the clone wakes up with the exact same session ID as the original match.
Oh, I see. So the database wouldn't know which match was which.
Precisely. They would violently collide in the system. The new session needs a completely unique ID and a fresh timestamp to reflect the moment the branch was created.
So he needs almost everything to be identical, but like a tiny fraction of the data needs to be custom tailored the moment the clone is born.
Yeah, Margaret explains that this requires a specialist. You need a way to step into the cloning process and tell Python, hey, copy the board, copy the player histories, but swap out the ID and the timestamp on the way out the door.
And she draws this wonderful visual on a whiteboard to explain it.
So she does. It's such a great analogy. She sketches a factory assembly line, a conveyor belt carrying objects. And smack in the middle of this belt, she draws a robotic arm labeled deep copy.
That visual totally stuck with me, because if you just call Python's standard deep copy command, Python checks your code to see if you've explicitly defined that special deep copy method.
Right, it looks for the instructions.
And if it doesn't find one, the robotic arm just stays asleep. The factory runs on its default settings and stamps out a perfectly identical problematic clone.
Exactly. But the moment you write that method into your class, you wake the robot arm up. You physically seize the controls of the clone machine.
You literally step onto the factory floor and reprogram the machinery. But taking over that kind of core functionality is incredibly powerful, and I'd imagine introduces massive structural risks.
Oh, huge risks. You can't just hijack the cloning process without understanding the safety protocols the factory normally runs in the background.
Here's where it gets really interesting. Because in any serious application, data doesn't just sit in isolated boxes. Objects point to other objects.
All the time.
I was thinking about this, and imagine Object A is a computer folder that contains a shortcut pointing to folder B.
Okay, tracking with you.
But inside folder B, there is a shortcut pointing back to folder A, like two people pointing at each other in a funhouse mirror.
Yes, a classic circular reference.
Right. So if a dumb copy machine tries to open every folder and duplicate whatever is inside, it opens A, sees the shortcut to B, goes to B,
It's just a shortcut to A.
goes back to A. Wouldn't the machine just infinitely click back and forth between those two folders until the computer completely runs out of memory and crashes?
It absolutely would. That infinite loop is the silent killer of custom clone methods. If the clone machine blindly follows every reference path, it falls into a bottomless pit.
This sounds terrifying for a developer.
It is. The only reason standard default copies don't crash our servers every single day is because Python operates with a built-in safety net.
Okay, what is the safety net?
In the story, Timothy notices Margaret passing a very specific parameter into her code. It's simply the word memo.
A literal memorandum, like a ledger.
Exactly like a ledger. It acts as Python's don't repeat yourself list. As the robotic arm is moving along the conveyor belt, duplicating nested lists and dictionaries and player profiles, it meticulously logs things.
Logs what, exactly?
It logs the memory address of every single object it successfully copies into that memo dictionary.
So it's checking the ledger before it does any actual work.
Every single time. Before Python attempts to copy a new piece of data, it queries the memo. If it sees an object it recognizes.
Meaning it says, hold on, I already built a clone of folder 3 steps ago.
Right, it stops. It completely refuses to duplicate it again. Instead, it simply grabs a reference line and points it to the clone that is already sitting over on the new assembly line.
Oh, wow. So it just wires the new clone directly to the existing reference. It's not drawing new dots, it's just drawing a new connection to a dot it already painted.
That's a perfect way to visualize it. And that single ledger entry grounds the recursion so the factory doesn't just spontaneously explode.
Okay, so we know the objective. We need to be the specialist who customizes the clone. And we know the safety mechanism. We have to respect the memo ledger. But how do we actually do it?
This raises an important question about execution. How does one actually step up to the keyboard and command the machine?
Right. Margaret lays out a 4-step framework for this, doesn't she? She calls it the specialist pattern.
She does. And step 1 is to create an empty shell using a command called cls.newCLS.
Okay, let's pause right there. Because if I'm a developer who usually just types my class, what is new actually doing? Why not just create a fresh object the normal way?
That distinction is the bedrock of the entire pattern. Think of building a house. New is a construction crew that pours the concrete foundation and puts up the bare walls.
So it allocates the raw memory in the computer.
Yes. And then init, the initialization process, is the interior designer who comes in right after. They paint the walls, set up the default variables, and maybe log a message to a server saying a new house has been built.
Wait, so if I'm trying to clone an existing chess match, I definitely don't want the interior designer showing up and blasting a notification to the server that a brand new match just started.
Precisely.
Yeah.
You are cloning a match that is already halfway finished. You don't want those default setup behaviors firing off.
That makes total sense.
By explicitly calling new directly, you lock the interior designer out of the building. You bypass the init method entirely. You are left with a perfectly uninitialized hollow shell in memory.
So step 1 says to create an empty, uninitialized instance. And being uninitialized is so crucial here because it gives you a perfectly blank slate to build the clone.
Exactly. It's a blank slate for the specialist to work with.
Okay, so we have our hollow shell. I assume step 2 involves that safety net we just talked about.
Spot on. Step 2 is the register phase. Before you even begin filling that hollow shell with data, you must immediately register its new memory address into the memo dictionary.
You write it in the ledger before the paint is even dry.
You absolutely have to. You are telling Python, listen, I am currently constructing this new object. If you run into any circular shortcuts pointing back to this tournament session while you are digging through the nested data, don't try to build a second one.
Just point them all to this specific shell.
Exactly. That prevents the infinite loops.
So we have a registered empty shell sitting on the conveyor belt. I assume step 3 isn't me manually writing code to copy over every single chess piece, player name, and timer setting.
Oh, definitely not.
Because that sounds like a miserable way to spend an afternoon.
It really does, and Margaret knows you don't want to do that.
Yeah.
Step 3 is just called deep copy. You simply hand the heavy lifting back to the machine.
So you let Python do what it does best.
Right. You tell Python's default copy.deepcopy function to iterate through the old object's attributes and pour them into your new shell.
And the machine handles all the tedious duplication.
Yeah, 99% of it. Carrying over the complex board states and move histories safely.
It basically fills the empty house with cloned furniture.
Yep.
Which leaves us with step 4.
Step 4 is manually set. The house is built, the clone furniture is inside, and now the specialist steps in for the final touch.
The custom tailoring.
Exactly. You manually override the specific attributes that need to be unique. You generate the brand new session id. You stamp the object with a fresh start time.
So to recap, create the blank slate, log it in the ledger, let Python fill the slate, and then tweak the unique variables. That is an incredibly elegant pipeline.
It's beautifully structured.
But so what does this all mean? I mean, I look at this 4-step manual override, dealing with memory allocation and recursion ledgers, and I have to ask.
Is it too much work?
Yeah. If Timothy literally just needs to change a single session ID so his database doesn't crash, isn't this massive overkill? Why not just write a quick method called branch match that copies the data and changes the ID in 3 lines of code?
Margaret actually entirely validates that instinct. She introduces a vital concept here called engineering judgment.
Oh, I like the sound of that.
She makes it crystal clear that just because you have the power to seize the robotic arm on the factory floor doesn't mean you should be doing it for every minor task.
Because sometimes a simple workaround is the best code.
Often it is. If you only need to branch a chess match once in a blue moon, writing a standalone .branch match or .refresh method is infinitely cleaner.
And probably easier for the next developer who inherits your messy code base to read and understand.
Exactly. You don't want to hide complex logic inside a dunder method, those double underscore methods, if you don't have to.
So when does the developer actually pull the trigger on the full specialist pattern? When is it worth the effort?
You only reach for this intense level of customization when you need that behavior to be the global standard.
Meaning you weave it into the very fabric of the language.
Right. If any developer anywhere in the company imports Python's standard copy module and tries to duplicate a tournament session, they automatically get a unique session ID.
Even if they don't know your custom branch match method exists.
Exactly. It becomes foolproof. You are building safety constraints directly into the foundation of the object itself.
That is the essence of that Victorian library craftsmanship we talked about earlier.
It really is. The object knows how to handle its own replication safely, regardless of who is asking it to replicate.
And what blew my mind as I read further into the source material is that this philosophical partnership with the clone machine doesn't just stop at deep copies.
Not at all.
If you need a different kind of clone, there's a different robotic arm waiting for instructions.
Yeah, if we connect this to the bigger picture, Margaret offers Timothy a sort of architectural cheat sheet to expand his toolkit.
Oh, right.
The first one she mentions is copy.
That's for shadow copies, top-level stuff, right?
Yes. Sometimes you don't want the factory to recursively drill down into every single nested folder and duplicate absolutely everything. Sometimes you just want a new top-level container.
Like having a list of player profiles. A shallow copy gives you a brand new list, but the profiles inside that list are just references pointing back to the exact same player data in memory.
Exactly. And if you want to intercept that specific process and add custom logic, you wake up the copy robot arm. The pattern is identical. The depth of the duplication is just shallower.
Okay, so that handles memory cloning. But what happens if the chess club server physically loses power? Like a clone sitting in active RAM just disappears.
Poof, gone.
If Timothy needs to freeze that chess match and save it to a hard drive so he can reboot it tomorrow, deep copy isn't going to help him at all.
No, that requires serialization. Taking a living, breathing digital object and flattening it into a string of bytes that can be safely written to a disk.
And then bringing it back to life later.
right? A process we call deserialization or rehydration. Python uses a different robotic arm for that called set state.
Because waking up from a hard drive is very different than being cloned in memory.
Drastically different. Think about it. When an object wakes up, its environment might have changed completely. Maybe it was frozen on a Monday, but it is being rehydrated on a Thursday.
Oh, true. If that object has an internal timer, it's going to be horribly confused.
It might even crash the server. But by defining set state, the specialist can intercept the wake-up process. You can tell the object, okay, here's your frozen data, but before you fully wake up, check the current system clock and adjust your timers.
It's like giving an astronaut a debriefing the moment they wake up from cryosleep before letting them touch the ship's controls.
That is a brilliant way to conceptualize it. You manage the state transition, but the cheat sheet concept that requires the most mental gymnastics is reduce.
Yes, the pickling mechanism.
Yeah.
This part was fascinating.
It's so clever. Python uses a module called pickle to serialize data, often to transmit it across a network to a completely different computer. But here is the massive hurdle. Some things physically cannot be pickled.
They call them unpickable resources, right?
Exactly.
Like a live database connection. If Timothy's chess match is actively streaming, moves to a server over a specific network socket, you can't just copy that live socket connection, turn it into text, and email it to someone.
No, because a network port on your machine doesn't exist on my machine. It is physically bound to the host hardware.
Right. If you try to blindly pickle a live database connection, Python will throw a massive error and just crash.
So how does the specialist get around this? You intercept the pickling process by defining reduce, but reduce doesn't try to save the object.
It does something much cleverer. It saves the instructions.
The blueprint, exactly. Reduce returns a tuple, a little package containing a callable function and the specific arguments needed to run that function.
So you're essentially telling Python, listen, don't even try to pack this live database connection in the suitcase. Instead, pack this piece of paper.
And on this paper, write down the database URL, the username, and the command to establish a new connection.
It's like, instead of trying to freeze a living, delicate plant to send in the mail, which is obviously going to rot and die in transit, you just mail a seed.
A seed along with a highly detailed set of watering and soil instructions.
Exactly. The receiving computer gets the package, unwraps the seed, reads the instructions, and automatically runs the function to establish a brand new, healthy database connection on its own local hardware.
You completely bypass the physical limitation of the resource by abstracting it into a recipe.
It gives you total mastery over how your creations travel through the world, which is just so cool. And that brings us beautifully back to the emotional core of this narrative.
Back to the library.
Yeah, at the end of the article, we are back in that quiet Victorian library. The clocks are ticking. Timothy has successfully implemented the 4-step specialist pattern for his deep copy.
He runs the test script. He watches the factory belt move.
He makes a clone of the ongoing chess match. And the player histories carry over perfectly. The complicated board state is identical.
But the session ID.
The session ID blinks into existence as a brand new, completely unique string of characters. The database accepts it without throwing a single collision error.
The perfect custom clone.
And Timothy has this profound realization. He looks at Margaret and says, it's not just a copy anymore. It is a descendant.
A descendant. That specific word choice is so powerful. It implies lineage, but it also implies evolution.
Right. It's not just a carbon copy stuck in the past.
Exactly. It acknowledges that the new digital object has a deep structural relationship to the original, but it possesses its own unique identity. It has its own path forward in the system.
And for you listening to this, I think that is the ultimate takeaway. Writing code or interacting with any complex technical system isn't just about memorizing a library of commands.
No, it's not about typing copy and just crossing your fingers that the default settings don't blow up your server.
It is about deeply understanding the factory floor. It is about stepping up to the robotic arm and giving your digital objects a memory, a lineage, and exact instructions on how they should be born into the world.
It shifts you from a mere consumer of a programming language to an active partner in its execution.
Beautifully said.
And as we wrap up this deep dive, I want to leave you with a final thought to mull over, building entirely on that concept of reduce and the seed analogy we just discussed.
Oh, the idea of saving the instructions rather than the physical object? I love that.
Yes. Think about how we manage our own lives and systems. We live in a world that is increasingly obsessed with hoarding massive amounts of raw data.
We save everything, every file, every redundant image.
Every massive artifact filling up petabytes of server space just in case we need it later. But how much more efficient could our computing systems, or frankly, even our own personal mental workflows be, if we stopped trying to perfectly archive every single heavy object and instead just learned to brilliantly save the minimal instructions for how to rebuild them when needed?